Hello, everyone. So today we're going to take what we now know of quantum mechanics and apply it to real molecules that have more than two atoms. So today, however, is going to be focusing mostly on notation. So we've already described how we can take atomic orbitals and use them to form molecular orbitals. But here's the problem. We've only applied this to systems that have two atoms and nothing more. So we're going to be trying to expand this idea as we go to molecules that have two atoms to molecules where we aren't limited by the size of the system. Unfortunately, to do so, we're going to have to make some brief notational changes. So the first thing I want to go ahead and acknowledge is that we can pretty much construct our molecular orbitals from any linear combination of relevant atomic orbitals. So I'm not just limited to combining two wave functions with the relevant coefficients. I can extend this to 3, 4, 5, 10, 100 orbitals. So we can actually build our molecular orbitals over large network systems, hundreds of orbitals, and this is actually a fairly common thing. And what's important to note is that our molecular orbitals are likely going to be spread over atoms that don't have to be next to each other. We just have to make some brief limitations when we're trying to think about how I'm going to build up a molecular orbital system. The first of which is, well, the molecular orbitals don't necessarily, or atomic orbitals don't necessarily need to be connected. There has to be some line of connection between the various atomic orbitals involved. So the classic example of this is sigma and pi networks. So if I have two p orbitals, for them to be able to interact, say in a pi system, there has to be pi bonds going all the way through the entire molecule. And similarly, I can have a sigma network that can correspond over an entire molecule. So a good way to think about what will make a sigma network is this is going to be almost all of the bonds in a molecule that we could hybridize using valence bond theory. So if I can hybridize it, it means it can make a sigma bond, which means it's part of the sigma bonding network. If it's a p orbital that's left out, a valence p orbital that's left out of the sigma network, it likely is going to be in some form of pi network. The question is whether you're making one, two, or more pi networks. And we'll talk about this idea a little bit more later. It is worth noting that what I have not included is core electrons. So you can indeed build in core electrons as part of molecular orbital theory, but as we've seen before, core electrons tend not to have very significant overlaps or interactions with neighboring atoms. So as such, while they should technically be included in MO theory, they're often dropped out for convenience or just for simply having to deal with less orbital mixing. So with this idea of here's what I'm talking about when I'm talking about a molecular orbitals, it's just going to be some combination of some arbitrary number of atomic orbitals. Let's go ahead and revisit exactly how have we been solving our molecular orbital energies. Because remember, trying to determine our MO energies was the key part of trying to solve this system. Once I have my MO energies, I can do things such as figuring out the compositions and then the compositions of my molecular orbital or its exact form simply through knowing those coefficients and how much of any given atomic orbital will contribute to the larger molecular system. So as a reminder, in order to solve for the energies of my diatomic system, we made use of our secular equations. And specifically, in order to solve for the energies, we often started by ignoring the coefficients and simply focusing in on the determinant of our various energies of interaction. So hopefully this matrix nomenclature looks fairly familiar. This was the set of equations we used to solve for our original energies off of a diatomic system. So what I have presented here is a heteronuclear diatomic system where I have my two starting atomic orbital energies, their um, the resonance integral, and their overlap integral. And from these, we can determine the possible energies for our orbitals. But you might notice that this is a little bit problematic because this notation explicitly says that it turns out that the overlap I care about is the overlap in between the only two atomic orbitals possible, A and B. And that my resonance is also that same interaction because nothing else is possible. Now, as you may note, this is going to be a bit hard if I go up to a system with 3, 4, 5, 6 atomic orbitals, because this matrix is going to get really big really quickly, and how am I going to keep all of my variables straight? And so the first thing we're going to focus on today is how I need to change my nomenclature to help accommodate for solving systems of much bigger networks. So the first thing we're going to do is replace a lot of our variables in our secular equations for more general forms, where we're going to have Hamiltonians essentially represent applying our Hamiltonian to our relevant system. And as you're going to notice, a lot of these terms are going to be analogous. I'm replacing my Coulomb integral with a Hamiltonian integral. And the same thing with my resonance integrals. And we're going to talk about this a little bit more. But again, the major point I'm going to be developing this new nomenclature is the fact of now I'm very explicit about which orbitals are interacting, whether it's in terms of a Hamiltonian or if it's in terms of a resonance integral. But now I know exactly which two atomic orbitals are interacting, which is going to be very useful when there's more than two. Now, let's go ahead and dive a little bit more into the notation and what each of these three major expressions are telling me. So here's essentially going to be what each is that each of these various symbols is representing an integral. So the first and foremost is hxx, whether it's AA, BB, whatever the term is representing my Coulomb integral. Or in full integral form, I'm applying my Hamiltonian to wave function x, and then applying the complex conjugate. So again, a good way of thinking about this is the expectation value of the energy of orbital x. So this is the energy of orbital A. This is the energy of orbital B. This is wonderful if orbitals A and B are eigenfunctions. However, they rarely are. So it's often better to think about these as expectation values instead. Now, what gets a little bit more problematic is when we have AB and BA. In this case, these are our resonance integrals. So this is applying the Hamiltonian to wave function y and then the complex conjugate x of x to the same result. And so again, this is that same idea that we have to deal with the fact that if x and y are centered on two different atoms, that this value, that they aren't necessarily going to form an orthogonal set, which means that this value might not be zero, as there may be some energy of interaction. So again, in the diatomic form, this is equivalent to our beta term, which becomes very important as we're trying to solve energies of systems. And then we have our good friend, the overlap integral. So this is literally just how much the wave functions in x and y overlap. If I've got two orbitals centered on the same atom, this guy will go to 0. If they're the same orbital, then congratulations, because all of our atomic orbitals should be normalized, this value will go to 1. However, this gets very tricky if, as we've seen before, if x and y are centered on different atoms. But we can often use arguments of symmetry and physical representations of overlap to spot where this might be a 0 value, as in no overlap can occur, or much more rarely 1, as in we have a perfect overlap. But unfortunately, most of the time, this is somewhere in between and is occasionally quite problematic. Now, in this case, E is representing the energy of the wave function. So in this case, since this form is describing a molecular orbital, this is going to be the energy of the arbitrary energy of any given uh, molecular orbital. However, in practice, what we're going to typically be solving for is the energies of individual molecular orbitals. Now, to represent the fact that I may have molecular orbitals of 1 or 2 for mixing 2 orbitals, or this may I may end up having 4 different orbital energies if I'm mixing 4 atomic orbitals, 6 energies if I'm mixing 6 atomic orbitals, and so on and so forth. So we're often going to solve for an arbitrary, the energy of the arbitrary molecular orbital n. So what we can then do is, by looking at solving for the energy of the arbitrary molecular orbital n, we can now, instead of expressing the secular equations in the determinant form, express them in their full equational form that we introduced at the beginning of molecular orbital energies. So this is the full, most arbitrary way of describing the energies of a diatomic system. So again, we have our Coulomb integrals, we have our resonance integrals, and we have our overlap integrals. Then we have the energy of wave function n, and the the important to note, we also have our contributions of atomic orbital A to molecular orbital n, and the contributions of atomic orbital B to molecular orbital n. And this will we can use these contributions to determine the probability of the wave function being found on atom A, B, or C, simply by taking the square of these values, as this will turn our coefficients back into the probability expressions. And again, for completeness sake, we are still representing the overlap integrals of AA and BB, though it is worth noting that whenever you see the overlap values on these diagonals, they are going to have a value of 1, which we are going to make use of quite frequently through the next couple lectures. So one of the useful things we can do with this notation is we can use these sets of matrices not only to solve for the energy of each of the to solve for the energies of each of the possible molecular orbitals, but we can also then, using these energies, solve for the configurations or coefficients of the various atomic orbitals that will give a molecular orbital of that energy. So hopefully this makes sense. If you need a little bit of review, feel free to go back to the lectures on the diatomic system, where we started establishing these nomenclatures. And hopefully you can, if you're still having trouble, you can compare and contrast the two nomenclatures. But now what we're going to be doing is trying to solve this net set of equations for our energies and our orbital coefficients. So what's going to be then very useful is, because let's be honest, this matrix is a little bit messy, is that I've got a subtraction element in each of my matrices, which means that I can actually split this matrix into 2. So I can take it as the matrix of the Hamiltonian, so my Coulomb integrals and my resonance integrals, minus the overlap integrals times the energy, and then all of the difference of these two all multiplied by my coefficients. Now, one of the things that is very worth noting is that once I split this matrix into 2, what we then find is that every single one of these elements contain the energy of orbital n, which then lets me pop out this value of En out front, because at this point it's just a constant that's shared by each of the elements of the matrix. So then what I'm left behind with is 3 matrices: a Hamiltonian, an overlap, and a coefficient matrix. And because, let's be honest, nobody wants to be writing these whole matrices all of the time, especially because these are often not simply 2 by 2 matrices, but can scale to much larger sizes. we're going to often shorthand these matrices using simple variables. So I'm making use of bold lettering to make note that the fact that these are matrices and not individual elements. So the bold H is now representing the Hamiltonian matrix, which is more or less a compilation of my orbital energies and my resonance integrals. Then we have our overlap matrix, which is literally the overlap of each of the orbitals with all of the other possibilities. In this case, if I have a 2x2 system, it's just the overlap of an orbital with itself or the overlap of the two orbitals with each other. And as you note, because of the symmetry of our wave function nomenclature, these two diagonal elements should be equal. And the same thing for these two Hamiltonian values. So this is actually going to become useful as we proceed later on. So it is worth noting that there is a certain amount of elegant symmetry involved in all of these matrices. And then finally, we have the coefficients of each of the atomic orbitals that goes into making the molecular orbital n. So in practice, if I have a 2x2, this will have values of 1 or 2, and we'd end up having a listing of the coefficient of atomic orbital A in molecular orbital 1 and coefficient of atomic orbital B in molecular orbital 1. So this value is actually going to really be telling us everything we need to know about my physical molecular orbital wave function. Well, these are telling me about the energies, and this is telling me about the interaction of the individual orbitals. So there's a lot of information contained in each of these elements. So one of the nice parts about using this condensed nomenclature is that I can take this big equation and drop it down to a couple simple variables. As I can express this long form as the Hamiltonian matrix minus the energy of orbital n times the overlap matrix, all of this times the wave function itself. And because of the secular equation, we know that this all has to equal 0. Now, when I have one side equaling 0 and a subtraction in the middle of a term, it's often useful to split this up into halves. And that's more or less what we're going to be doing, is we know that the Hamiltonian times the orbital wave function is going to produce the energy times the orbital wave function with this added factor of the overlap matrix. Now, hopefully you should note that this looks rather similar to the Schrodinger equation, where I apply my Hamiltonian to the wave function to get the energy times the wave function back. Really what this what the overlap matrix is letting me deal with is the fact that I might not necessarily have a set of eigenfunctions, and so I might have to modify my wave function in order to get my energy back. So it gets a little bit messy, but we still have the fundamental features of our Schrodinger equation still there. Now, what can be particularly useful is the fact that I can then turn this, instead of being an equation just for each of the individual molecular orbitals, to an equation for the entire molecular system. So if you remember, the entire set of molecular orbitals can be essentially constructed by combining all of the possible molecular orbitals together. So this sounds a little bit confusing, but the general idea for a 2x2 system is that my Hamiltonian is going to stay intact. But now what happens is, instead of having Cn as a row vector, what I've now done is added in an extra row for all of my other elements. So this first row is telling me how much of orbital A is in wave function, is in the first molecular orbital. The second column is telling me about how much of orbital A is in my second molecular orbital. And if you had a third or fourth molecular orbital, each element would be telling you how much of A is in each of those MOs. So this is actually quite useful. And as you'll notice, it is going to show up on both sides. Now, the last interesting feature is this term. The energy is now no longer the energy of a single molecular orbital, but instead it's going to encapsulate the energies of each of my molecular orbitals. Now, what's actually quite unique is that my energies are representing what we call a diagonal matrix, where all of my off-diagonal elements have a value of 0, and my only values are on the main diagonal. So this is actually quite useful when we're trying to do matrix multiplication, and we'll be making use of it quite frequently as we go on. Now, it's one of the reasons why we do really enjoy this form is it is a quite condensed method of showing our secular equations. Now, it turns out that if you want to express your full secular equations, you can regenerate them quite easily simply by conducting the matrix multiplication of each element on the left side and setting them to the matrix multiplication of the right side. And when you do this, you get a quite large matrix, where again, this whole first matrix, we've got 4 elements, and these were generated simply by doing the matrix multiplication of my Hamiltonian times my wave function. And this second matrix on the right side of the equation was generated by taking the matrix multiplication of my 3 elements. So there's a lot of information in this set of equations, but it's worth noting that when I'm dealing with matrices, the major reason why I'm doing them is for purposes of linear algebra. And the reason why we call it linear algebra is it means that I'm able to put together a series of linear equations. So I have a series of variables, for example, in this case, my coefficients, or in truth, my actual atomic orbitals, and I have to solve 4, 5, or 6 equations all at once. And matrices are just a very convenient way of demonstrating it. And a way to evaluate this full set of secular equations is simply saying that what I'm doing when I'm setting 2 matrices equal to each other is more or less I'm setting 4 equations equal to each other. So I can regenerate my 4 secular equations by taking, say, the upper left element on my first matrice and setting it equal to the upper left element on my second matrice. And so by setting these 2 equal together, congratulations, we regenerated our first secular equation. You can then do the same thing with your upper right elements, your lower left elements, and your lower right elements. And by doing this, we end up generating a set of 4 equations, which we now need to figure out how to solve all at once. Now, we've done this procedure a little bit more stepwise when dealing with a diatomic system. But the beautiful part with this notation is it's fairly easy to extend to a triatomic, or to a system with 3, 4, or 5 atomic orbitals. Because at that point, we just have a 4x4 matrix, a 4x4 matrix, a 4x4 matrix, a 4x4 matrix, and a 4x4 matrix. So it doesn't become any harder, it just becomes a lot longer. So we typically need to make use of some fairly specialized computer softwares. So what we're going to be doing next time is extending this new notation to our new set, to a new problem as we try and deal with a pi network that's distributed over 4 atoms. However, in order to solve this, we're going to need to start making some rather severe approximations. And we'll be doing that next time as we start Huckel theory. Till then, take care and stay healthy.